Hello everyone. So let's look at a problem which is more often asked in interviews. So trapping rainwater. So we need to find how much water we can collect, and you can say that these are the pillars, and whenever the rain comes, how much of the water can be stored between these pillars. So as you can see, at this position there will be no water stored as there is no pillar here, left side of it. Between these pillars this much of water can be stored. This will overflow. Similarly, this will overflow, and this. So you can see that this is the water that can be stored in this pillar. So can we see, now we have to see how we are storing water at each position. So let's say at this position I want to find how much water can I store. So is there any pillar greater than this? Because only that much water can be stored. So there is no pillar greater than this on the left side, then we know that water will overflow. So we can leave that. In this position, I know that we have a pillar here and I have a pillar here. So whichever is the minimum of these two, that at that level we can store this much of water. Now once we come across this pillar, we know that there is no pillar greater than this one. So on the left side, there is no pillar greater than this, so all water will overflow. And now for this position, there is pillar greater than this, and there is also a pillar greater than this on the right side. So we can store how much water? The minimum of these two. So this much water can be stored here. For this much water can be stored, and for this much water can be stored. So we can see that for any position I, the amount of water that can be stored here is the maximum on the left side, and we have to find the maximum on the left side and the maximum on the right side, and then whichever is the minimum of these maximums, we can just subtract it from the height of I, and that much water we can store. So this is maximum this position, and this is the left maximum, and the minimum of them is L. So L minus height of I. So if this was, suppose this, so we can say L 2 minus 1. So 1 unit of water can be stored here. If this is 0, so 2 units of water can be stored here. So similarly we'll do for others. So what we are seeing at is we have to find the left max and the right max for each element. So for each element we have to find left max and the right max. So the naive approach would be, for this element we'll traverse through the whole list and find the right max and also the left max. So for each element we are traversing n elements, and there are total n elements. So it would be n cross n, big of n square. So by doing this we are having a time complexity of big of n square. Now what else can be done here? So we can find the left max and the right max in just one iteration. So suppose we are at index this, so we'll store one variable left max. So for this index the left max should be currently 0, so we'll set it to 0 for this element. Now once we come here, this height is 1, so it is currently greater than 1, so the left max would become 1, and its left max is 1 now. For this element we'll compare it with the left max, it is 1, so its left max should also be 1. For this element it is greater than the left max, so left max now becomes 2, and the left, this there would be 2. Similarly for this the left max is 2 and this height is 1, so left max here would be 2, here also 2, here also 2. For here its height is greater than left max, so the left max would be 3, 3, 3, 3, and 3. Now for finding, we have found the left max by traversing just one time for all the elements, and we are storing these in an array. Now similarly we can approach from backside and find the right max of all the elements. So so this element's right max would be 1. For this it would be 2. Now this we compare it with 2, and for this it would be 2. For this it would be 3. This it would be 3. This would be 3, 3, 3. So we have now found the right max and the left max of all the elements in just one iteration. One iteration for left max and one iteration for right max. And then we can just, for each element we can traverse once again and then subtract the values. So minimum of, we have to find the minimum of 1 and 3 and then subtract for this height. So this is 3 and this is 1. So minimum of this and this is 1. So no water can be stored here. Similarly we can do, so the water stored element is minimum of left max, right max minus water at that position. So in this we have taken 3 times of n, and this is big O of n. So we are able to solve this problem big O of n. So I have already implemented the solution. So here we are first traversing and then storing all the left max in left max array and right max in right max array by traversing from back, and then we are storing for each element. We are seeing how much water we can store there, and then just returning the total amount of water that can be stored. So this was the trapping rainwater problem, and this is generally asked in interviews.